So we are going to discuss about work, energy, and power. Okay, before coming to these terms, we have to discuss one more thing about vectors. We have already discussed about the basic things about vectors, and we have discussed addition and subtraction as well. Now we are going to discuss about product of two vectors. So there are two scenarios where, let's say, there are two vectors A and B. So these two vectors can give a scalar result if they obtain their products, and in other case they can give another vector as a result of multiplication. So based on the results obtained, we can say whether it is scalar product or dot product, and we can say whether it is vector product or cross product. So in this particular video we will be focused on scalar product or dot product. This one we are going to discuss in the next uh, chapter. So a scalar or dot product is where two vectors, let's say A dot B, these two vectors are going to give us scalar result. So let's say this is vector A and another vector B. Let's say this is vector B, and if the angle between these two vectors is theta, we can write their scalar product as magnitude of vector A multiplied with magnitude of vector B multiplied with cos theta. You can write it AB cos theta, or you can write it BA cos theta. So this is one way to represent dot product of two vectors A and vector B. Okay, if you see carefully, this is B cos theta. This is magnitude of the projection of vector B onto the vector A. So if you obtain projection of vector B, and if you say this is the projection, so B cos theta is this magnitude. So in other way, we are saying that magnitude of vector A multiplied with the magnitude of the projection of vector B on the vector A is dot product of vector A and vector B. Or we can take it in this way also, where this is A cos theta, which is magnitude of the projection of vector A on the vector B. What I have written here, A cos theta is the projection of vector A, and this is magnitude of vector B. So A dot B can be represented in this way also, where we have multiplied the magnitude of vector B with magnitude of projection of vector A, and was in other way magnitude of vector A into magnitude of the projection of vector B on the vector A. Okay, this A dot B or scalar product, we can say that ax I cap plus ay j cap plus az k cap. What I have done here, I have resolved this vector along I cap, j cap, and k cap into its magnitude. That is along x axis, y axis, and z axis. So in this particular case, we are using Cartesian coordinate system. In the same way, we have to expand this thing in terms of its components. So bx I cap, by j cap, and bz k cap. And this will be ax I cap dot bx I cap, which will be 1. I dot I will be 1. So we can write ax bx plus ay by. Other terms are going to be eliminated, as I dot j will be 0 and I dot k will be 0 as well. So we will have the terms I dot I, which are with I dot I, and j dot j and k dot k. So ay by plus az bz. Okay, why I am saying that I dot I or j dot j and k dot k will be 1 and others are 0. I'm just explaining. So here we have Cartesian coordinate system. This is y-axis, this is z-axis, or you can call g-axis also, and this is x-axis. So the unit vector along x-axis is I cap, the unit vector along y-axis is j cap, and the unit vector along z-axis is k cap. If you are doing I dot I, that is magnitude of vector I, which is 1, that's why we call it unit vector. So 1 into 1 cos theta, and now the theta, which is the angle between I and I, will be 0. So cos 0 will be 1. It will be ultimately 1. In the same way, j cap dot j cap will be 1, and k cap dot k cap will be 1 also. So in this way, and if you go for I dot j, so we will get here angle 90 degree, and then I dot j will be 1 into 1 cos 90, which is 0, so it will be ultimately 0. In the same way, j dot k will be 0 and k dot I will be 0. So this thing I have used in the previous discussion here. I dot I is surviving, and then it is x dx, and others are 0. Now we are going to discuss work energy theorem. We are going to develop the concept of work and of course energy here. So let's take a scenario. Let's take that a body starts with velocity u, initial velocity, and we are doing it in one dimension for timing. So initial velocity u, and it reaches up to here with final velocity v. So if it has velocity which is changing, then an acceleration is working on it. Okay. Now if this is s equals to 0 displacement, and here displacement is s, that is this displacement is s, we have a simple relation here, which is v square minus u square equals to 2as, or you can say v square by 2 minus u square by 2 equals to a into s, or you can say m, I am multiplying m both sides, mv square by 2 minus m u square by 2 equals to ma into s, and ultimately we will have mv square by 2 minus mu square by 2 equals to f into s. Okay. Now, if we observe this thing carefully, what is happening? We know that a moving body has energy, which we call kinetic energy, and energy is nothing but ability to do work. So, if a body has some amount of ability to do work, we call it energy. So, if a body which is moving, and due to its motion, by virtue of its motion, it has some energy, means it has ability to do some work, and that energy we call kinetic energy. So if there is something changing in kinetic energy, it means whether this body has done some work, or maybe some external work has been done on this body. So if we are observing these two things here on left side, here left side, and here on right side. So on the left side, we can see that something changing, which is related to motion. Okay, and this thing is equal to something forced into displacement. So what we can say about these two things, on the left hand side, it's motion related thing, and on the right hand side, there is force involved, and with this force, there is something displacement also. So we can say that on the left hand side, here kinetic energy is changing, and here work is done. And this is what work energy theorem, that change in kinetic energy of a moving body is related to work done. Okay, whether this body has done, or maybe some external energy has been working on this body. So what is here next? This is kinetic energy, change in kinetic energy, and this is work done. And this is what work energy theorem says, that delta K, this delta we use for changing term, change in kinetic energy equals to work done. Okay, so with this matter of fact, this is final kinetic energy, mv square by 2, v is final velocity, that is uh, energy related with its motion in its final stage, and this is energy related with its motion in its initial stage. So this is kinetic energy, and this is final kinetic energy, and this is initial kinetic energy. So final kinetic energy minus initial kinetic energy is change in kinetic energy, and here something happening. Maybe some external agency is doing some work on this moving body, or maybe this body can do some work and it can lose some kinetic energy. So this is what happening here. Force, displacement, these two terms are related to work done. So we have discussed this all thing in one dimension. We can do the same thing in 3D also. So in three dimension, we can do 1 by 2. I'm writing here mv square. We can write it simply final kinetic energy. Okay, so in 3D, here we have discussed in 1D so that we were not bothering about the vectors. But in 3D, change in kinetic energy equals to force dot displacement. That is what it means. It means that the component of force acting along the displacement. Maybe just uh, what's the direction of displacement, or along the direction of displacement, or maybe uh, it is acting against the displacement. It depends. We are going to discuss about those things also when we go to discuss work in detail. So the final thing is here, I'm just summing up what we have discussed here, that if there is a moving body, it has some ability to do work, and if somebody has ability to do work, we can say that it has energy, and due to its motion, this capability of doing some work is due to its motion, so we can say this is kinetic energy. So if there is some change in kinetic energy, means some work has been done. This is what change in kinetic energy equals to, and how much work has been done. This work done is equal to the change in kinetic energy. The change in the ability of the body of doing work is the work done actually. So this way we are going to say that change in kinetic energy is equal to work done. So this is work energy theorem. And in 3D, this change in kinetic energy is F dot S. Means you can say the projection of force along S. So this one multiplied with the magnitude of S. Or you can say the projection of displacement along force multiplied with the magnitude of force, as we have discussed already. A dot B in uh, in the respect of projections. So this is work energy theorem. Now we should take one example, and of course after that we will come back to the discussion of work again, detailed discussion. So let's take an example here. We have two different vectors here, f and d. One is force vector and another is displacement vector. So we have to find out angle between these two. So we can write f dot d, which is, look, I already have discussed about component forms. So it will be fx dx, fy dy, and fz dz. And what is here? Fx is this much. This is fx, x component of force, and this is fy. This is minus 5 fz. So we can write 3 fx into dx, 3 into 5, 3 into 5 here. So I'm writing directly. So 15 here, 4 into 4, that is 16 here, and minus 5 into 3 is minus 15. So it will be 16 unit, whatever be the unit here. Okay. Now we know that f dot d is f d cos theta also, where theta is the angle between the vector f and the vector d, and that angle we have to find out. So if we want to know this thing, this will be equal to 16 units, and f we can find out from here, as we have one thing, f dot f is f square, we already discussed. So f square, this will be 3 square f dot f, fx into fx plus fy into fy plus fz into fz. That will be 3 square 4s plus 4 square plus minus 5 square. So 9 plus 16, that is 25, and here 25. That will be 50. And then we have f equals to under root 50. In the same way, d will be under root 50. You can check it by yourself. So here we have to write under root 50 into under root 50 cos theta equals to 16. So cos theta equals to 16 by 50. Under root 50 into 50 will be 50 here. So theta will be cos inverse 16 by 50 only. Okay. One more thing is there. Also find the projection of vector f on vector d. So this will be f cos theta. So f is under root. This is f cos theta. The second part is projection of f. So this will be under root 50 into cos theta. Cos theta is 16 by 50. That will be 16 by under root 50, whatever be the unit here. Okay, so we have solved this example actually. Now moving to detailed discussion about work. So we have already discussed that work is something related to force and displacement, and in three dimension it is F dot D. Of course, you can use this thing in two dimension and one dimension as well. But in general, if we are working in three dimension, we can write F dot S also. And then let's say we have a body here, and we are applying a force F here. This is F. And this body moves up to this distance, and this is, let's say this is displacement s, and the angle between these two vectors is theta. So work done will be f dot s, that is f s cos theta. F is the magnitude of vector force, and then s is the magnitude of this displacement vector, and theta is the angle between these two vectors. Okay, this is one thing. We can write it as work equals to f cos theta into s also, that is projection of vector f, that is projection of force vector on displacement vector. So in this way we can represent force vector, and then cos theta will be multiplied to give projection of this force vector multiplied with displacement. This is work done. You can use this thing also, fs cos theta, or you can use f cos theta into s. Both are same actually here. Now, actually we have to go from here to here. That will be better. Now we have different scenarios here. Look, what if the angle between these two vectors, that is theta, is 90 degree, that is force is perpendicular to the displacement. In that case, cos 90 will be 0 and work done will be 0. What is the scenario? This is if force and displacement vectors are perpendicular to each other, or if there is force but displacement is 0. In that case also we will have no work done because of this force. And of course we have another way where force is 0 and body is being displaced. So in that case also there is no work done because there is no force, so it is not going to do any work. Okay, this is one thing. Now, based on this angle theta here, look, if theta is less than 90 degree, we have the component of force along the displacement, and there is another case. If we have force which is making more than 90 degree, this theta is greater than 90 degree. In that case, if say this is the force, let's say F1, so its projection will be opposite to the direction of this displacement vector. So in first case, where the component of force is along or in the direction of the displacement vector, we say positive work done. That is, theta should be less than 90 degree. And then we have negative work done when theta is greater than 90 degree and we are moving up to 180 degree. So less than or equal to 180 degree. Okay. So in that case, when theta is greater than 90 degree and less than or equal to 180 degree, then this force has component just opposite in the direction compared to the direction of displacement vector, and then work done by this force will be negative. And you can check it mathematically too. If you are putting here theta something greater than 90 degree, it will be uh, a negative value here, so work done will be negative at the end. Okay, now moving to one more example. Here we have the example. It is well known that the raindrop falls under the influence of the downward gravitational force and the opposing resistive force. Okay, I'm just explaining what is the situation here. So suppose a raindrop starts falling. It accelerates with an acceleration due to gravity, which is uh, we can take here for simplicity 10 meter per squared second. Okay, then it will keep accelerating. But there is another force acting on this raindrop, which is drag or resistive force due to air. So that drag force opposes its motion, and the force is proportional to speed of this drop. So there are two forces acting on this raindrop. One is force, gravitational force, which is due to gravitational pull of the earth, and another is resistive force, which is due to friction of this raindrop with air. So with these two forces, it has to come to the ground. So what is the question here? The question is, if the raindrop is falling from a height of 1 kilometer, that is 10 to the power 3 meter. Let's say this height is 10 to the power 3 meter, and mass of this raindrop is 1 gram, or you can write mass equals to 10 to the power minus 3 kg. I'm just converting all these things into SI system. Okay. What is happening? It hits the ground with a speed of 50 meter per second. So if the final velocity of this raindrop, let's say V is 50 meter per second. So we had to find out the work done by the gravitational force and then work done by the unknown resistive force. Actually, we know this resistive force. What is it? So this is it, drag. So we have to calculate work done by the gravitational force. Okay, let's take first case where we are not considering the resistive force. We are considering only gravitational force. For that reason, we know one thing: v square minus u square. U square initial velocity square, and if it starts from here, u equals to 0 meter per second, of course. So that thing is 0 equals to 2g into h. Gh. So V equals to V square equals to 2GH, and this is 2 times G we take for simplicity 10, and then H is 10 to the power 3. Now we can get the kinetic energy. Look, this is in the absence of whatever it is feeling. Okay, in the absence of resistive force. What we can do here, we can multiply 1 by 2 into mass of this raindrop, and here also we can do 1 by 2 into mass. I'm not writing all those units here, but you know that mass has unit of kg here, and this is meter per square second, and this is in meter. Okay, ultimately it is going to be joule because these are all energy terms, or you can say work. So what is happening here? This will be 10 to the power minus 3. So this thing and this thing, this is we can write m only. Okay, because at the end we have final kinetic energy without any resistive force will be 10 joule, and this is what you can say work done by gravitational pull, work done by gravity or gravitational force. Okay, so if there is no resistive force or drag force, the final velocity we can give this way: v square minus u square equals to 2gh, and then we can obtain 1 by 2 mv square, that is final kinetic energy, and we know the change in kinetic energy is equal to work done. Here the kinetic energy of this raindrop is increasing due to external work done by gravitational pull on the raindrop, and that work done is 10 joule. Okay, what if we consider that there is resistive force? So let's take the second situation when there is resistive force. For that reason, here we have final velocity given already. Look, 50 meter per second. So final velocity is 50 meter per second. Mass is given here, which we have converted into SI system. So the in the presence of in the presence of drag, we have final velocity 50 meter per second, and mass is 10 to the power minus 3, and the final kinetic energy will be this much, half m and v square here. Okay, so it will be 1 by 2 into 10 to the power minus 3 into 25 into 10 to the power 2. I am writing here 2500, instead I am writing 25 into 10 to the power 2, or you can write it 1 by 2 into 25, this is in joule, into 10 to the power minus 1, or you can write 2.5 here, and this will be 1.25 joule. Okay, so if there is no drag, the kinetic energy will be 10 joule, but due to this resistive force, the kinetic energy remains up to 1.25 joule. So we can take a difference here, and that difference will be 10 joule minus 1.25 joule, and this will be something 8.75 joule. Okay, this much work has been done by the resistive force. Work done by the resistive force on the raindrop. And then this much work, that is 10 joule, this much work has been done by the gravitational pull, but the final energy remains only 1.25 joule. That is, there is a work done which is opposing this gravitational pull. That work done is due to the opposing force, that resistive force, or you can say drag force, and that work done will be equal to 8.75 joule. Okay, and this should come minus 8.75 joule if you go in accordance with the final kinetic energy minus original what it should be, and if you do it will be negative. This shows that this work done is reducing the kinetic energy of this raindrop. So I hope you got the idea what is happening here and how can we get these answers for these questions. So in case you have any confusion or doubt, you can ask in the comment section, of course. Let's discuss a little more about units of work done or work. So we have a formal definition: work equals to F into S in the simplest form. force kg meter per square second, and into s this will be kg meter square per square second. This is SI unit of work done, and we write it as joule, capital J. Okay, what if we have to obtain the dimensional formula? This will be ml t to the power minus 2 into this is length, so it will be L square. This is dimensional formula for work. Okay, there are other units too. Other units you can take in CGS system. There is erg, and we know 1 joule is 10 to the power 7 erg, or you can say 1 erg is 10 to the power minus 7 joule. We have other units like calorie, of course, which is used. So 1 calorie, you can write 1 calorie 4.18 and 6 joule. And we have some smaller units for this work, and that is of course these units we use work and energy both. So we have electron volt, and 1 electron volt is 1.6 into 10 to the power minus 19 joule. So in this way, okay, we have a larger unit also, that is kilowatt hour. Okay, after getting concepts about power, we can derive this unit also, which is 3.6 into 10 to the power 6 joule. Okay, and this one we are going to derive if it comes in future. So we have obtained dimensional formula, we have obtained SI unit. Now we are going to end our discussion with another example. Let's take this example. So we have a question: a cyclist comes to a skidding stop in 10 meter, and during this process the force on the cycle due to the road is 200 newton. What is happening actually? Cyclist, let's say this is cyclist, this is skidding, and it skids up to 10 meters, and during this process it experiences a force opposite to its displacement of skidding, and that force is 200 newton. Now we have to say how much work does the road do on the cycle. Okay, so force here and displacement here. So work done is 200 newton, that is force, into displacement, that is 10 meter. And if you think what is the angle between these two, it will be 180 degree. So cos 180 degree, which will be minus 1, and then it will be 200 joule, but negative sign. So there is a negative work done on the cycle by the road. Now, how much work does the cycle do on the road? So what happens here? We have discussed three different cases when there is no work. So in one case, there is a 90 degree between force and displacement. In another case, there is force but not displacement. So you can say, and there is another where there is no force. So there is no work done if there is no force. But what is happening here? In this particular case, there is force. There is a force applying by this cycle, uh, but the ground is not moving due to that force, or opposite to that force. Ground is stationary here, so we can say that okay, S is 0 in that case. So if S is 0, no matter force is there, the work done will be 0. So if we ask what is the work done by the cycle on the ground, so this will be 0 because S is 0 in this case. So I hope you have got some idea about work and energy. Of course, with this example, we are ending our discussion here. We will continue in the next, in the next video, we will continue, uh, more about kinetic energy and of course potential energy, and we will relate with work done. Those all things, and moreover, Till now, we are discussing only force to be constant. We have discussed anywhere force. Suppose here 200 Newton. This force is constant. So in next video, we are going to discuss how can we determine work done when there is a variable force. So see you.